So that was the first question I asked you is about to what extent machine learning can be incorporated into science. And
Yeah.
uh, yeah, so we discussed that. I want you to comment on what I just said too, because why my critique of Jan LeCun's assessment. All right. But first, I'd like you to let's talk about the next question. All right, and then we'll
Yeah.
all right. So the next, I want you also to talk about the next question, and perhaps simultaneously just tell me what you think of
Okay. Okay.
these last few remarks. So what I
Mm.
said about Jan LeCun, what he said, and his comparison of machine learning and alchemy, as in alchemy
Mm.
predated modern chemistry, so machine learning will
Yeah.
predate some more coherent, serious form of mathematical computational modeling, and essentially. I said it's, just to put everything in a nutshell, if that analogy is to be borne out, you have to compare
Mm.
machine learning to past revolutions in mathematical modeling and in computational modeling. So that would be
Mm.
Euclid, that would be Newton and Leibniz, and for
Mm.
calculus, that would be abstract algebra to perhaps a lesser extent with Abel and Kronecker and Gauss and others. And finally, with the computing revolution, that is Turing and Gödel and von Neumann. And I said that the
Okay.
comparison just isn't borne out. Now, my next question to you, and I want you to tell me what you think of that too. All right. But
Mm.
first one, the next question that we discussed the last time was specifically about. Uh, Actually, we ended up discussing machine learning first. All right. So
Yeah.
data science is basically learning.
Second.
Yeah. Sorry.
Mm.
So however,
No, go.
data science is basically machine learning plus a few other topics like linear regression,
Okay.
statistical
Mm.
analysis.
Mm.
Basically, so a
Yeah.
lot of people say
Yeah.
it's just a new word for statistical analysis that uses computers. Uh,
That's kind of a stretch, but okay.
Yeah. So
Mm.
why don't you tell me what you think of statistical analysis on the whole? Actually, so last time around we discussed machine learning, statistical
Yes.
analysis, and computing. Basically, the idea of taking in a large amount of data and giving a model as an output, a mathematical model or
Yes.
computational model as an
Yes.
output.
Yeah.
What do you think of that? And that's the thing I'm most skeptical about. That's the thing I don't believe in. And you and I have discussed
Mm.
this at length in the context of Bacon, right? So, what do you think of
Yes.
the idea? Bacon is a very great proponent of it. He felt data was everything, though he lived,
Mm.
400 years before the invention of
Yeah.
modern computers. What we hear every day
Yes,
these days is
not exactly data, but he was saying rather than you have come up with models based on what you observe, based on what you actually see and observe, rather than trying to superficially guess, come up with a theory. Use the observations you've made, like rock solid observations you've made, and come up with a theory.
right.
That's his way of saying it. Just like
Yes.
believe in data. Yeah.
Yeah. So that's where. So here, this is the question. All right. Do you know that I
Mm.
don't believe that a great amount of data is actually going to help anyone give a coherent model,
Yeah.
because all the great theories have required very little data, right? And the last time around, I gave the example of how you're able to basically predict infinite amount of data, the motion of a particle in Newtonian mechanics,
Mm.
with if you're just given its initial position and its initial velocity, you're able to create an infinite, and of course the forces. You
Mm.
have if you have some good expression for the force law, and
Mm.
you're able to basically produce infinite amount of data. That is the value of x at every given point in time, t, right? You're able to get that
Mm.
from just these very sparse pieces of data. So
Okay.
and all through science you see this. That's part of the roots of my skepticism, where you've never in history have we needed so much data to create a model, to create a theory. And
Mm.
really, scientific success has never been judged also in terms of data coverage in that sense. But anyway, so putting aside my views on the subject, what do you think on the idea of needing a lot of data, doing statistical
Okay.
analysis and
With
outputting a
machine
model?
learning, sorry to
Okay.
interrupt, but yeah, with machine learning, there's a misconception that more data means better predictions, which if you have any good idea of machine learning or some foundation aspects of machine learning, even though that's not true. There is a problem called overfitting, where you don't want it to, if you put too much data into it, what will happen is the relationships between two variables won't make any sense. They'll be so varying that it will make zero sense. So we don't want that. We want a relationship that we can understand, that we can predict, and surely say, yes, this is good. But at the same time, you don't want the results to be too biased, meaning too less data. So we wanted to teeter that line. And usually when you take a machine learning course, it basically tell you to do analysis between overfitting and underfitting. They'll tell you to balance your biases and your variances. So find parameters that suit that, give initial parameters in such a way that you don't underfit and also you don't take too much varying data. And this is given a lot of importance because in a way that, how do I put this? This is one of the foundational aspects of machine learning, especially for predictive systems. Forget facial recognition everywhere, facial recognition, pattern recognition everywhere. You want even the most foundational problems in machine learning, you have this idea that what I am going to do with the data. And based on this, you'll have a lot of methods, test data, training data, and so on and on. You choose the kind of data you want to train, you choose the kind of data you want to test, and you choose the kind of data you want to actually, before you send the algorithm out for real time data inputs and, see how it works. So you want to, figure out parameters based on data. So thinking that machine learning works with a lot of data is kind of a misconception. It's not. But regarding overall, generally, regarding statistics that and relationship with data and seeing, modeling things based on data, I'm kind of on the fence. Because one reason is it's proven to be a legitimate science. Number one, it's not something that's nonsense. It's not something that's completely idiotic. It's legitimate. There is something really, something very interesting going on with just reading data and trying to come up with models based off of it. There's something really good with it. But at the same time, we don't, how do I say, we don't have a lot of alternatives to it. Taking machine learning out of the picture, that is, we don't have a lot of great alternatives to traditional statistical modeling. And on top of it, statistical modeling has worked absolute wonders when it comes to physics. If you take a look at or what do I say, in fluid mechanics, which I work on, when you take hydrodynamics, for example, you can see a macroscopical picture of a bunch of particles or fluid flow, how water flows, and you give macroscopical equations and get results and predict the fluid flow for that. You compare that with a microscopical viewpoint where you use statistical mechanics, you use Maxwell-Boltzmann statistics and all that kinds of stuff. There is this amazing, agreement between these two completely different approaches. So you take a microscopical view, you use statistical mechanics to get there, and you take a macroscopical view where you use partial differential equations and with vector calculus and so on, and you combine them both. You take these two different approaches, you'll be stunned to see that they both come to the same results. You will see that they almost bridge the gap between individual particles and continue, like discreteness and continuous things. So statistics, if used correctly and used in the correct context, it works wonders. Even though you might think it's not great modeling. I'm not relegating statistics to just looking at data, putting some graph. No, there is more to it. There is, there's an abstractness to statistics than just, looking at real life data and calculating variance and, more rather than like a statistical, like an economical aspect of it. Economics people do statistics, people who do sociology, statistical studies, those kinds of things. I'm not just relegating it to that. I'm seeing statistics as a wider field where you have a more abstract nature of viewing things. You just look at, okay, here's a set of points. How do these points behave? Just randomly saying things. That's true statistics. But if you look at it as, as a machine learning person would do, they won't look at it like that. They will look at it like house pricing and square foot area and stuff like that, and for them and see what modeling there is. But I would understand why people would go for that, because it has more real life applications, real life implications to that. But for me, statistics is a valid science, and it's I'm hoping you're talking about it in my context as well, as a physics context as well, and not just for some some trend, showing some trend or displaying some trend. It's not just that. Statistics is much more. There is much more to it than there's that. But I'm kind of unsure whether Bacon talked about statistics in this generalized sense, or about data in that generalized sense. Whether he talked about it in an abstract sense, or was he just saying calculate, observe, record, and find a relationship. I don't know what he's meaning. I don't know whether he's just mentioning that part of statistics, or whether is he talking about the more abstract part of it. So that's my take on it. I'm seeing it as a valid science, but I'm seeing it mainly because as a valid science because of its abstracts.
Okay, all right, interesting. All right, so first, the thing over here is, all right, so let's go through these points one by one.
Okay.
Because I'd like to talk about it. So one thing is, you begin with how data scientists are required to cut down on data and try. So this is what comes under the stage called EDA, right? Exploratory data analysis. Basically,
Yes.
what a data scientist has to do when he's trying to cut down on data is he or she has to take a look at all of the dimensions. They're called dimensions. Basically, if X is a variable they have to predict, they have to the output should be a model in which the value of X is predicted as a function of some number of variables, right? And before that, we have a ton of data, probably in the form of several tables with values of these variables. And the data scientist, as part of his exploratory data analysis, is required to start slashing them off, deciding what he doesn't want to use in his machine learning algorithm. So he reduces the number of dimensions. Yeah. So the keyword here is dimensions. Now, interesting thing is, first of all, right from Descartes, right? Descartes, who envisaged. Okay, sorry, I'm getting it wrong. I got it backwards. Descartes and Fermat, their lifetimes had a little bit of an overlap. I meant to say right from Fermat, people have been trying to study this question of on what variables is something we're trying to predict dependent on, meaning what data is needed in order to determine or predict the value of some parameter, like the apple falling from Newton's tree. I gave that example. The motion of a particle, we see it's dependent on, first of all, so a force law, an expression for the force law, and then the initial position. So the force law, then the initial position and the initial velocity, right? It's also dependent on the mass, and you can say the time at which you're trying to evaluate. So right from Fermat, people have been exploring this, because Fermat is the one who defined extremas, right? He is the one who started to understand that if you have a large number of variables, that is a parameter which is a function of a large number of variables. He devised a very simple test to see which variable is irrelevant, at least in a certain region, for a certain range of data, which variable is irrelevant. And you and I know the technical thing of that is just that the derivative should be 0 with respect to that variable, right? So within the range that the derivative is 0, we see that the variable whose value we are trying to predict just does not depend on that particular irrelevant variable. So people have been doing this from time immemorial. And if you look at the academic literature here, actually, I've been talking about the industry practices a lot, but here the academic literature is ahead. And if you take a look at the academic literature, there are perfectly well-defined tests to determine what variables are relevant or irrelevant just by looking at the data. You can just, in fact, you can even build I myself have built automated systems to do this. I don't do EDA by hand. I just run my code and it throws out some variables which are most relevant. Okay. So there are perfectly well-defined methods of doing this. So you're right in the sense that dimensions are, people would like to reduce dimensions, the dimension of that data. But as far as volume is concerned, the number of data points after you've restricted the dimensions, there it's definitely true that the higher the volume, the more data you feed in, the better your model is supposed to be. There's no doubt that there is a correlation between the two. Here more data means good in the tradition of Bacon. So the question about Bacon, right? Bacon, naturally, like I said, he lived 400 years before computers. He lived 300 years before the first serious thing of statistical analysis came about, before Galton and before Laplace and all of them. The reason I roped him, dragged his name through the mud just now, is he was a very reasonable fellow. There's no doubt about everyone should read Bacon. People should read Novum Organum and other things. What I meant to say was that his viewpoint resembles the viewpoint of proponents of machine learning today in the following crucial sense, that is that theories are basically provisional summaries of data. Right? They lose their validity, they lose any significance they have, according to Bacon, once you discover more data. Right? And a theory in the sense that some people have very eloquently said, like Bacon, should just be a summary of data, an efficient summary of data. Right? That is what Bacon was basically saying. So he was telling data is what's important. When you get more data, you get a more accurate theory, much in the same way that Jan LeCun or someone else might say. Of course, he doesn't say this, but most proponents of machine learning would say that more data means better model, right? In that sense, I'm not talking about the sense of dimensions. Fewer dimensions, great, but greater volume. The greater the volume of your data, the better your model is. So that is the sense in which I was saying that. Now, as far as statistics, so now actually all that we're talking about.
If I'm getting you right, you're saying that more number of parameters is not advisable, but more number of data on that particular set of parameters is fine.
Exactly. Precisely. They're not just fine. That is what you need. That's what you need to get a more.
That's the thing about, that's the kind of point I make about machine learning. Even if you do have favorable parameters, even we have just one parameter compared to the parameter, two variables which you want to do a relationship with, taking too many data into account is not very advisable, because even in those cases, if you look at real life applications,
overfitting,
even the most vital points of the most vital pieces of information regarding predicting something, even they have their downsides, where if you have very large set of information very large set of data regarding a certain parameter, which is extremely vital, you do have significant variations, significant fluctuations in your pricing. There might be there may be a whole set of freak data in there which can really muddle your predictions, and your predictions could be way off. In some cases, even if the variable is pretty vital to understanding or predicting some result. Even in those cases, it can happen. So I would disagree with using a large volume of data is going to be always beneficial. Maybe in some cases it might be beneficial. Like I'm saying, if you take it in a very abstract sense, the more number of particles you have, to simulate a fluid flow, the better your approximation is going to be. The more continuous it's going, the more better it's going to approximate the continuous fluid. In those abstract cases, in those specific cases, yes, a large volume of data points available for simulation is great, but not always when you consider what we think as statistical analysis. In those cases, it's not. But in a more physical modeling sense, yes, it definitely is very beneficial.
Right. And in data science, right? In physics, I completely agree with what you're saying, simulation.
Well, I'm not very well acquainted with data science, but...
Okay, for neural networks, let's just take some small thing of neural networks or any one of the...
You mean more nodes in a neural network is...
No. So yeah.
More input nodes, I mean.
More input in the sense that no, the same number of input nodes, same number of layers. Actually, in the sense you're talking about a bigger model, and I'm not talking about that, because even when you talk about more particles, you're talking about a bigger model.
Oh, you mean you're training the neural network several times with large sets of...
Exactly. The larger you're training.
Okay, got it.
Yeah, the larger.
Yeah, I would agree. Yeah, that's correct, right. There. In neural network sense, yes.
Right.
Most problems it makes sense.
Yeah, so that's what I meant. Okay,
But
actually,
but the thing is with neural networks is there are certain problems where you just need to train it once or twice, and you get really good approximations. And with
yeah.
the even with the correct kind of a networking, with the correct kind of network architecture, more optimal network architecture, you can even reduce the number of data required for it to train it.
Yeah. So here actually there's I mean, that's one thing I've observed when it comes to models for which neural networks work, in that wherever they seem to work with just when you train it once, no feedback or anything like that, you actually can you could have fit the data very well just looking at it. If you just showed it to talented, in fact, a talented 12th grader,
Yeah.
they'd have been able to fit it quite comfortably. When I used to teach classes to 12th graders on mathematics. There's some of them are able to do this, and I myself, of course, had a lot of fun with it in school. And you take a look at the quote, when Dyson. Actually, I want to speed this up. I want to go to the next question, which specifically focuses on your thing. And when Dyson went to meet Fermi, right, with his new theory, his new model for weak interactions or something like that, Fermi asked him, how many variables, how many free parameters are available. Free parameters in neural networks are the weights, right? And how many are there? There are in some of them goes up very large, but Dyson said something like 8. There are 8 free parameters. So in essence, Dyson had created this template model and trained it on the data that they got from the laboratories for weak interactions, particles.
Okay.
So at which point Fermi laughed and said he doesn't even need to look at Dyson's proposal, and he quoted von Neumann. Von Neumann said in a very interesting, in his characteristic way, if you allow me 6 parameters, 6 free parameters, I can fit an elephant. I can give you a formula to draw an elephant on a screen. And if you allow me to, you can give me 7 free parameters, I can make it wiggle its tail. Right. So basically, that's the kind of, so when it comes to these kind of models, I've noticed that you're able to do it without machine learning. All right. I'll draw something. All right. Yeah. So basically, that's my experience, and that machine learning only doesn't really contribute anything new in the cases in which you're able to train a piece of a model once and be done with it and get something quite accurate in it with that. But on the whole, yes, more data is generally taken to be good. And the phrase big data came about with this new facility of collecting a great deal of data. This is running just about everything today in industry, right? Having a ton of data, collecting a ton of data, mostly with our consent, the keyword being mostly, that's being fed into these high-level slick summarizers. That's what I would call them. I'd say machine learning sort of fits in with compression, right? That's what I've said, and I made this point before. That is that machine learning is perhaps misclassified as AI, and I would say it's better classified as probabilistic compression, or maybe even more appropriate, probabilistic hashing, right?
A more mathematical way of putting it, in my opinion, which I would think is way more appropriate than just waving a magic wand and saying AI stuff.
Yeah. So I don't think it comes under numerics exactly.
No, I know. It's more computational, like it. But when we look at computer science or computational aspects, it's more maths, basically, more foundational maths, which is like again a different kind of application to it.
Right.
Rather than just pen and paper, you give a more computational viewpoint, which has been fueled by the development of computer science itself in general, the basics of hardware and processors and ALUs. That fueled these kinds of things in mathematics. Now that's a revolution.
Yeah.
But coming to your question regarding whether machine learning is a revolution or not in maths, which was your first question, which you asked me before the statistics one. So regarding that, I would say there are 2 sets of questions whether we have to ask regarding machine learning before coming to the question. One is of course, this question whether machine learning is actual mathematics, valid mathematics, or is it a successor or does it come under that hierarchy of revolutionary ideas in computation and maths and numerics? That's one question. And if yes, then we go into a much deeper question whether such ideas of numerics, computation, and mathematics are actually valid ways of modeling physical concepts, which is a much deeper question, which we would have, if you have read Wigner's Unreasonable Effectiveness of Mathematics, you would know that it's a much deeper question. So saying that machine learning and applying it to science is a more of a vague question, but in fact, it's actually two questions, where first we have to think whether machine learning is an actual mathematical revolution. And if the answer is yes, can only we be going to the next stage of answering whether we reach a much deeper question, whether maths itself is an effective model of the physical world. So in my opinion, I would say instead of trying to answer whether machine learning is a good modeling strategy, if you're looking at it in a more research point of view, a more think of it more as a researcher or as a student, and you're trying to work out problems and solve problems of machine learning or physics, I would say do it. It's always going to be, it's always interesting and fun to see how well machine learning does, because I have seen it. People in my department or in the university here, some of my friends are working on prediction mechanisms of extreme events using machine learning models, and which seems to be a substitute for traditional nonlinear dynamical models, where they use nonlinear, they use oscillators and other nonlinear equations to predict systems. I've seen them use machine learning for that, which is very interesting. Using it as a substitute for, traditional maths for physical models is interesting as a researcher or as a student. It's great to work on, but in a philosophical context, I think you can approach it in any way you want. Either you can answer the question whether machine learning is actual mathematical revolution, or you can answer the question whether mathematics is an actually reasonable way of expressing physics or expressing physical systems. I would like to answer or give what I think my answer is for these two answers. One is regarding machine learning as an actual mathematical tool. In its current state, it's not. Saying machine learning as an actual mathematical, coming under the hierarchy of such great, revolutions in maths. I'm saying machine learning in its current state is not, but it has the capability to be that, because, like I said, the great strength for machine learning is its visualization. And with its visualization tool, when I talked about the linear algebra aspect of it, it's with a paper showing why it's Turing complete, why it can solve any kind of, or why it can simulate any kind of a Turing system. It makes it really powerful, and I think you can use the visualization principles, which I think we should learn more about in machine learning, rather than trying to just use neural networks as it is. Trying to come up with new ways of using such visualization tools to understand different aspects of linear algebra, and doing all that. Doing that to machine learning will definitely make it a revolution. And the principle behind it works, but not many people are working on it, in my opinion. Not many people are focusing on it, in my opinion. And working in that direction will definitely make it something amazing and something very interesting, and will definitely change maths forever. Because as far as we've seen maths as just symbols, and symbols as as matrices, and like I said, even matrices are a great visualization revolution in maths. Representing data as 2D arrays, and giving it a symbol, and tensors and all that kind of stuff are all representing points and information as in a different sense, and that opened up so many avenues in maths and so many different operations. The same can be done with machine learning if you focus on that aspect of representation, rather than just seeing it as already it's done, it's completed, it's perfect as it is. It's not. In fact, I would say what machine learning is just an infant name for something is much bigger. I think you should give it a much different name than just machine learning. I think it's a more constructive name for something that is much grander and something that's much richer and something that can be more revolutionary. So that is the answer for whether machine learning is actually valid mathematics. It can be. Now, coming to the other aspect of it, whether maths is actually a great representation of physical systems. We have had this conversation before in private, where I have said I have my skeptical doubts regarding it, but over the time I've thought about it and I have changed my perception, and I do think while I do have some while we do have some irregularities, or sorry, not irregularities, some differences in whether with the unreasonable effectiveness part of Wigner's article, I do think that mathematics is the best way to do it. It is the best way we have to do it, and whatever we come up with will ultimately turn out to be just maths. It's inevitable you will go in that direction. So we were debating about whether that is unreasonable, whether whatever you come up with, whatever way you come up with to describe a physical system is eventually going to be turn out to be maths finally anyways. So I think we have disagreed over the fact that whether it's unreasonable or not. And I've said it is pretty unreasonable because it seems so absurd that it should end up always like that, and we have not come up with something else. But you have argued that